Welcome to EDU World Space.
Hi there. So for this problem, we need to calculate the electric field at a point P that we are going to call P in this case, the point in red, that is caused by a long uniformly charged thread that is along the x-axis and a small charged sphere Q, which is in here. So to do this, we are going to sum the contribution or the vector sum of the two fields that is produced by both of these charges. So in this sense, we will have that since the thread is positive, then we will have an electric field only in the y component because it is an infinite thread, so all of the x component of the electric field cancel each other and we will only have vertical component. So this is the electric field caused by the thread, and the electric field, because of the charge Q, it will be attractive and it will be in the line that connect this to the charge and the point P. And this is the electric field produced by the charge Q. So with this in mind, we just simply need to write first what are the electric field produced by a line, a charged uniformly thread and point charge Q. So for a thread, we will have that the electric field is the following. We have this term and also the linear density over the distance to that point P, that in this case, we know that distance is 7 centimeters. This is y, that distance. And it is only has a component and a y component, so it is only in that direction. We set it positive because it is pointing upward. And for the case of the charge, it is something a little more complicated, but we could see in the figure, and this is also given in the figure, that this is the angle that we are given. This is the angle theta. And so to obtain the electric field produced by a charge Q in that point, it will be the usual electric field produced by a point charge, which is this, over the distance d squared. This is the distance from Q to the point P. And the direction of this is given by, we can see in here that this vector, if we translate it to the axis, it will be like something like this. So we will have that both components are negative. So then x component is given by the cosine of theta in the x component, and the y component by the sine of theta. So with these two, we can we can obtain the net electric field caused by these two charges. So the net electric field is the sum of the electric field because of the thread and the electric field produced by the charge Q. So we will see here that we can sum component with component. So we will have for the X component, this following, minus cosine of theta in the y part, plus in the y part we will have something a little more let me write in here. It will be something like this: 1/2 pi epsilon sub 0 lambda over y minus the y component of the electric field produced by the charge Q, and this sine of theta, and all of this in the component, in the y component. So once we have set this, we can first obtain the distance d. So the distance d, we can see in the figure, it will be this distance in here. It's like the hypotenuse of these triangles. So it will be the square root, or well, in this case, because we need the d square, we just obtain that. So it will be 0.07 meters squared. This is 7 centimeters in meters, plus we can see in here that this side is 5 centimeters plus 7 centimeters. That's 12 centimeters. That in meters is 0.12 meters. So that's what we have in here, squared. So if we sum these two, I'm going to put this right in here. So we will have 0.07 meters squared plus 0.12 meters squared. So this will give us 0.0193 meters squared. Another thing that we can calculate is the angle theta. And from the figure, we can see that we can obtain that using the function the tangent function. So the angle is given by tangent of -1, tangent of -1, the hypotenuse over the x component. So, well, in this sense, well, hypotenuse, no, the, let me put the figure again. It would be the vertical side of this triangle and the horizontal side of this angle. So it will be, as usual, the angle is the y part of that distance over the x part, or the x component of that distance. So it will be 12 centimeters over 7 centimeters. And putting this into the calculator, we obtain a value of 59.7 degrees. Now we have this. We can substitute for each component. To make it easier, we're going to do each component separately. So we're going to get first the x component of the net electric field, so that in here, in the previous expression, we know that this is only this term in here. So it will be minus the magnitude of the charge q cosine of theta that we just already obtained, 4 pi epsilon sub 0 d squared. And this is, we know that the charge, well, we know that this term in here, the inverse of that is 9 times 10 to the 9th newtons per meter square over coulomb square. We are also given the charge Q, which is, let me just say it again, it is minus 2Q, but in this case we need just the magnitude, so that will be 2 coulombs, cosine of 59.7 over d squared that we have calculated. It is 0.0193 meters square. Sorry. So this gives us a value for the x component of the electric field of minus 4.699 times 10 to the 11 newtons per coulomb. Now we need to obtain the y component of this net electric field, and that is this term in here. It is just this term in here, and that will be, can I put this in here to make it easy? So let me move this to here. And this is what we need to calculate in here. I'm gonna like in here. So we know all of this, and this is 2 times the Coulomb's constant times the given value for the linear density, which is 2.5 coulombs per meter. Also, we are given the distance, which is that distance, y, we know that is 7 centimeters, so it's 0.07 meters. And for the other term, we will have minus 2 coulombs over the distance to that point. Oh, also the coulombs constant, which is 9 times 10 to the 9 newtons per meter squared over c squared. And the distance to that point, which is 0.0193 meters squared, and this times sine of 59.7 degrees. So putting this into the calculator, we obtain a value of minus 1.622 times 10 to the 11 newtons per coulomb. So putting all of this into these two values that we just have obtained into the equation for the net electric field, we will have something like this. Of like the net electric field is just the x component in the y direction, in the x direction, and the y component in the y direction. So it will be minus 4.7 times 10 to the 11 newtons per second in the y direction, in the x direction, plus minus 1.6 times 10 to the 11 newtons per coulomb in the y component. And if we want to determine the magnitude and the direction of this vector, this net vector, we just simply need to obtain the magnitude of this vector, and after that the angle. So it will be like the square root of the x component squared plus the y component squared. So if we put the values that we just have obtained, this in here, theta squared, and this in here, theta squared, and after that we sum them and take the square root. So we will have a value of approximately 5 times 10 to the 11th newtons per coulomb. And the angle, just as before, we used the minus tangent function. So it is the y component over the x component. So we will have like something like this. Let me put it like in the way we can see that the negative sign goes away. So it was something like this. Newtons per coulomb over 4.7 times 10 to the 11 newtons per coulomb. So when we put this into the calculator, we obtain a value of 199 degrees. So this is the magnitude of the net force, and this is the direction of the net electric field. So this is it for this problem. Thank you.